Today, we're going to talk a little bit about shaker fundamentals. So, what is a shaker, right? Essentially, a shaker's a big speaker. So, let's talk about the major components in a shaker. So, first, we have the armature. The armature, and this is a cutaway diagram coming up. It's very simple, but the armature is the moving piece of the shaker. It's like the cone of your speaker. That's what you'll put your test article on. And then there's a voice coil. Voice coil is a copper wire or tube in water-cooled shakers that's wrapped around the armature. And that is going to have a magnetic field passed through it. You have the shaker body, which is typically made out of iron or some other kind of ferrous steel or something like that to better create magnetic fields. You have a field coil. In big shakers, this is another copper coil that is energized to create a magnetic field, static magnetic field. In smaller shakers, this is typically a permanent magnet. If you're less than 100-pound force, modal type shakers are all permanent magnet shakers. But when you get to bigger shakers, permanent magnets aren't enough to provide the force that you need. So we go to these windings that create this static magnetic field. Next, there's flexures. Typically, they're a J shape. This is what holds the armature to the shaker body, and these are flexible, so they move up and down, hence the term flexures. And this is keeping the armature attached so that the magnetic field isn't the only thing holding the armature in place. There's typically a guide bearing, especially in bigger shakers. Some manufacturers do things a little differently, but for the most part, they're generally a post in the middle of the armature that the armature can slide up and down on. All right, and that keeps the armature from tilting back and forth, which can be a problem because that causes cross-axial motion, which is generally undesirable in a single shaker application. Then there's typically some pneumatic load support. This is going to take the weight of your test article so that the shaker has more available force from the magnetic field to move around. Then there's typically some type of isolation mount between the shaker and the floor. Sometimes this is airbags. Sometimes the entire shaker body is bolted onto a large isolation mass that is also typically on airbags or is just a couple tons of concrete that's not going to transmit the vibration from the shaker into the rest of your facility. So when you turn on the shaker amplifier, the field coils get energized. That creates a static magnetic field. And then voltage to the voice coil is varied, which creates this dynamic magnetic field that'll move the armature relative to the field coils with the excitation that you want. Now, something that I don't have drawn in here is there's got to be some type of current lead that connects these moving parts, the armature and the field coil. It connects the field coil to the amplifier as well, so that current can get in here and cause that dynamic magnetic field that moves the armature. And how the force of the shaker gets calculated is based on this, right? So the force is equivalent to the length of this copper wire in the windings. It's the dot product between this, the length of the wire, and the cross product between the current and the magnetic field that's generated. Now, shakers have a performance curve to them, and there's basically 4 distinct areas of this performance curve. At the lower frequencies, the shaker performance is limited by the maximum stroke of the shaker. At mid frequencies, the velocity is what limits the shaker in here. And then when you get to these kind of mid to high frequencies, that is limited by the force or acceleration, right? F equals ma. So essentially, force and acceleration in this case are pretty much the same thing. And that mass component is the mass of your armature and your test article and everything in between, right? Head expanders, fixtures, bolts, nuts, et cetera, et cetera. And then you have the max frequency range, which is typically defined as 1.5 times the first armature resonance. If you look at ISO standard 5344, that's where this comes from. So you have this first armature resonance, and then when your shaker manufacturer says, okay, your shaker's rated out to 3,500 hertz, that is a frequency that's basically a little bit further on, basically 1,000 hertz in that case, of the 1,000 hertz past that first armature resonance. And we can see this is the performance curve of the shaker I'm using for this webinar. And we can see kind of how this works, right? You have this little blip here. And this is kind of the transition between the maximum displacement and maximum velocity. And then here is very clearly the first armature resonance. And then the maximum frequency here, 1.5 times that resonance. Now, keep in mind, this is log scaling. So this doesn't look like it's another half more, but really that's because it's log scaling. So the shaker resonance, the armature resonance here, bare table, is around 10 kilohertz. And the shaker goes out really to about 15 kilohertz. That's the rating here. This little shaker I'm using is good out to 15 kilohertz. And we can kind of see some things about this if I zoom in here. So this is an active picture that I have. And if we take a look here, I can integrate here and show you what's going on. So if I go to processing and integrate twice, you can see the displacement, and you can see how the highest displacement is at the low frequencies. And it just gets smaller and smaller, as you would expect, as we increase frequency. And if we look at velocity, we can see that limit as well. If I just do a single integration, you can see the frequency of peak velocity here is around 40 hertz. And there's this little plateau here where we're maxing the velocity of the shaker. And you can see that if we look at the acceleration curve. If we go back to acceleration, you see there's this little blip here where we're going from velocity limit to force limit. And now we can see how this kind of works. This is just a couple of lines that I drew here. It's actually a sine reference profile that I created. And you can see clearly the transitions here. But if you run your shaker up to the maximums that it can do, you'll see these transitions like this. Displacement to velocity to max acceleration. So this is a constant displacement of 0.16 inches up until a constant velocity of 10 inches per second up to a constant acceleration of 5 Gs. So if these were the limits of your shaker, this would be the maximums that it could do. This would be the maximum profile that it could run. And keep in mind, of course, that this is all bare table. Any of the shaker specifications are all based on bare table performance. So once you start adding mass, of course, you're going to have less available acceleration. And you can see how this kind of resembles that shaker performance curve to a certain extent. If we go back, you can see I have this kind of transition here with reaching the shaker limits for the voltage that I'm put in. How I generated this curve we'll get to in a couple seconds. Well, maybe not seconds, but a couple slides at least. Other things that you want to keep in mind when you're looking at a shaker or doing shaker testing is that the rated force of the shaker must exceed the required test force. You don't want to try and do a test on a 6,000 pound force shaker that requires 6,000 pounds of force to do the test. Okay, so that's 6,000 pounds of force. What we're talking about is 600-pound test article at 10 Gs. That's going to give us 6,000 pounds of force. And if you have a 6,000 pound force shaker, you're really not going to be able to do that test. You want to have about an 80% margin there, or well, I guess you'd say a 20% margin. You don't want to run a test on your shaker that exceeds more than 80% of the force rating of the shaker. And the reason for that is you want to have overhead to be able to control. So if you're at your maximum here, and again, if we go back to this performance curve, if you're at your maximum here, then you don't really have any room to control anti-resonances and resonances and dynamics of the test article. Random shaker force is also something that you have to keep in mind because your shaker manufacturer rates the max random force relative to the bandwidth of the shaker. So in this case, let's call this a 50-pound force shaker. 50 pounds of force is over this entire usable frequency range. So if my shaker is rated out to 15 kilohertz, but I'm running a test from 20 to 2 kilohertz in random, I do not have anywhere near the maximum available force in what's called that narrow band excitation. So keep this in mind. Approximately, you're derating your shaker of that narrow band over the full rated bandwidth of the shaker times the max force of the shaker. Sine is different because we're not exciting all the frequencies all the time. So if your shaker manufacturer says 100 G max in sine, well, you're going to get that maximum at each one of those frequency lines that you're exciting. The other thing to keep in mind is the heavier your DUT is, the less max acceleration you have. It's this trade-off. The force remains constant, but if you increase mass, the available acceleration goes down. So that's another thing to keep in mind when you're running shaker testing. Also, cooling is very important. For every 100 degrees Celsius that the shaker armature is increasing, you get an increase of 40% in copper wire. Okay, so cooling is very, very important. That's why larger shakers move to things like water cooling as opposed to air cooling, which is used in lower force shakers. So right around 20,000 pound force is when you start seeing water cooled shakers. The interesting thing here is if you have an air cooled versus a water cooled shaker and everything else is the same, the armature is the same, the field coils are the same, everything's the same except one is water cooled, and that's typically done by having the armature winding done in copper tubing, and then water flows through that copper tubing on the armature while the test is running to cool it. If the only difference is water cooling versus air cooling, you're going to get more force out of your shaker than just an air-cooled shaker. So it's kind of an interesting thing about shakers. And you see with some manufacturers that are doing multi-shaker type applications, what they'll actually do is use hydraulic oil to absorb heat. And they can get a lot more force out of a smaller shaker by submerging it in that oil and pulling heat away through the oil. It's a lot more absorbent of heat than just air cooling, and also a bit less of a risk than water cooling sometimes when you have multi-shaker setups and have a lot of stuff that you're dealing with, and sometimes you have that hydraulic compressor and everything already available, so it's integrated into the design of some of these things. Pretty cool stuff. Another thing to think about in talking about controlled shaker testing is average control. Average control is when you take two or more accelerometers and average them together for the control spectrum. And it's helpful for a couple reasons, but typically when you have strong resonant anti-resonant pairs, and this is kind of a great example of that. I've got one accelerometer in one location that's going up. I've got an accelerometer in another location that's going down, and I can average them together and say, okay, so in between these two accelerometers, I'm getting my target spectrum, my target vibration. And this is great use case for this. When you're testing on a slip table, a lot of times the vibration closer to the bull nose is more than the vibration that you get at the end of the table. And a lot of times with these large slip tables, it comes with a single tapped hole that you can screw a control accelerometer on. And for most tests, sure, that's fine, but it's kind of a misnomer that, and this is kind of common thinking, that on this slip table or on my head expander, if I tell the shaker to do 1G RMS, that I'm getting the same vibration everywhere across this. This is kind of an assumption that we make when we're doing these tests, and it's not true. The slip table, as well designed as it might be, is going to have some dynamics itself. So it's going to have areas on node lines that don't do much vibration. It's going to have antinodes that do more vibration. Okay, so sometimes what you might have is a fore aft setup for your control accels, where you're measuring acceleration up here and measuring acceleration down here and saying, okay, if I'm getting 1.5 Gs here and a half a G here and I average them together, then on my DUT, it's a 1 G. Also, if you have a particularly large slip table and you have a slip table that maybe is older and doesn't have great guide bearings in it, it has a little wiggle to it. Sometimes you might want to do two control accelerometers along the edge of the slip table instead of just that one central point. So random averaging is based on the average PSD of the individual control sensors, and sign averaging is based on the linear average of the amplitude of each control sensor, depending on what the amplitude estimation method is. Long story short, sign is not an FFT-based algorithm for determining what the amplitude is at any single point in time. It's extracted directly from the time data. So there's 4 different ways to do that. We have harmonic, which is a tracking filter, which filters out harmonics. And then there's peak, average, and RMS. You might also pick extremal control, which takes your designated control accelerometers, and from that pool, it's going to pick, based on whether you choose minimum or maximum extremal control, it's going to pick a single accelerometer as your control amplitude. It's typically used when responses are not to exceed specified values, or under test or over test needs to be avoided. If you want to avoid under test, you'd pick minimum control, because that's going to give you the lowest amplitude out of the pool of control accels and increase your drive to get more excitation. So you pick minimum for under test if you're concerned about under test, or you pick max if you're concerned about over test, because max is going to take your pool of accels and use the amplitude from the one that's reading the highest, and then reduce your drive level so that the excitation is as low as it possibly can be out of the whole pool of control accelerometers. All right, I am going to go in here and run the shaker in the way that I did to generate this shaker performance curve that I came up with. And what you can do is if you do this test in the same way, the transfer functions should remain the same throughout the life of the shaker. If something changes on that performance curve, you might want to call your manufacturer and ask him to come in and take a look. Okay, so, and especially if you have this resonance peak that shifts significantly, you might have an issue with your armature that has a crack, or the winding is delaminating or something like that. You'll get a different looking curve. So the first thing to talk about is the setup. I have a drive cable here, and there's a T. One end of the T goes to the shaker amplifier. The other end of the T comes into an input channel. And what we're going to do is control on voltage in this case. And then the other is set as a measurement channel that's going to your control Excel that's installed in your typical location on the table, wherever you typically put a control Excel. If you're doing this periodically to evaluate shaker health, then you want to make sure you're putting the Excel on the same place every time you run this test. All right, so let's take a look at Test Lab. And you can see I've got my Excel set up here, and I have control on voltage, and that is teed off from my drive. So what I will do here is first I'm going to run a dwell, and I have my dwell set up to run at a fixed frequency at 100 hertz. And what I'm going to do is I'm going to adjust my amplifier gain. So I'm going to modify, I'm going to tweak the amplifier gain knob until I see the acceleration that I want here. So I'm going to do this sweep, and I'm going to do it when I see 2 Gs at 100 hertz. When this comes up here, I'm going to hit start. And now you can see the voltage is coming up, but I've got no response here. And now I'm going to start increasing the gain on my amplifier, and you can see that G level start to come up. Okay, so now I'm at 1.2 Gs right here. You see? Maybe I can make this a little bigger. There it is. Cursor, properties, and we'll increase this text here. There we go. So 1.2, all right, I'm going to go up till I hit 2 Gs very slowly. Keep in mind that some of these gain knobs on your shaker amplifiers are logarithmic. So now I'm at 2 Gs, right, at 100 hertz. So now I've calibrated my amplifier to get the value that I want at 100 hertz at the given drive voltage level. And I have my drive set to about 50 millivolts. Okay, so I'm going to hit stop here. And now, without touching anything, I'm going to run a sine sweep. Okay, so I'm going to go into sine control. I'm going to hit arm. And I'm just going to start. I'm running at 4 octaves per minute. Just for time, it takes about 3 minutes to run this whole sweep. You might want to run this a little slower to get a better characterization, but here we go. So remember, I am putting out a constant voltage, all right? And we will see down here the response of the accelerometer. And you can see I already have my cursors on here from the last sweep, and I'm pretty much at the same exact values that I was before for that max velocity number. I think on the slide I was at 40 inches per second, or I'm sorry, it was at 40 hertz. Yes, the accelerometer is on the armature. Bare table, it's mounted right into the very middle of the armature on this shaker I'm using. And right about now is basically the most annoying frequency to me. I don't know if you can hear it coming through or if the noise suppression is wonderful on, well, I'm going to cover my ears for a second here. All right, now it's beyond the point where I can hear it with my old ears. But you can see my resonance on this sweep was exactly the same as the resonance in the sweep I did earlier, and that's what you would expect. And let's take a look at that. We'll start a new one here. So this is from today, and what I got here? The last one, let's see, Friday. Yeah, so they're pretty much right on top of each other, more or less. If there was any significant deviation between this setup and the next setup, then that's when you'd be concerned. That's it for me. Thanks, everyone.